Hello students, welcome to today's session on work energy theorem from the unit work energy and power. The derivation is also very important, and also the various pathways through which we are calculating work has majorly asked multiple number of times in the CBSE boards and the competitions also. So let's consider the work energy theorem. What is it? Consider this diagram if you can consider it. Yeah. Change is allowed. This situation where a body is shown is in translation motion on a curvy linear path. If the path goes like this, but the body is moving translationally. That means straight. On a curvy linear path, the path is curvy linear, so it's increasing speed. Those are the stipulations associated. So speed is increasing. Now the net force acting on the system or the body must have two components. Yes, it will have two components. One will be the tangential component, which is necessary to increase the speed. The speed is getting an increment, and the normal component, which is necessary to change the direction of the motion. Okay, because normal is causing the change in the direction of the motion. When we are applying Newton's laws of motion in an inertial frame, where inertia can exist, you can call it for a tangential summation of m times a, because force, as we all know by Newton's second law, that it is F is equal to ma. Okay, and Newton's laws are all prescriptive of F is equal to ma, and normally it is the integration of m times a, and that means the normal integration. That means the acceleration which is occurring on the normal axis, and here too. Okay. So let the body start at position 1. If the body is starting at position 1 with speed v1 and reaches the position 2 with speed v2, and in an infinitely small path of increment is represented by this vector, the work done by the net force during the process will be work 1:2. Okay, that means the work which we are calculating from that particular path, it will be integration of f dot ds, where we are adding up the two components. The two components of the force be force tangential and force normal. So these two components we are adding, we are giving it a dot product again of ds. That means we are calculating work for the first system. We'll be getting a close integration where the lower limit is 1, upper limit is 2, ft dot ds. Similarly, when we are calculating it for, when we are substituting the things into the work formula, we will be getting close integral of v1 to v2. That will be the condition when we are calling, this statement is particularly called the work energy equivalence, or the work energy theorem, where we are integrating it from v1 to v2 mv dv. That means we are taking things to be constant, and v dv we are getting v square, v2 square minus v1 square. We are substituting the values. That means if we are considering kinetic energy to be half v1 square, half mv square, then half mv2 square is the final state of the kinetic energy, and half m v1 square will be the initial state of the kinetic energy. And yes, we are giving it a subtraction. That's representation of the two kinetic energies. Yes. The terms half m v1 square and half m2 v2 square is representing the kinetic energies, because the formula half m v square. Yes. And for work 1 to 2, we are getting the kinetic energy has to be kinetic energy 2 minus kinetic energy 1. This above expression is depicting as the work done by all the external forces acting on a body in carrying it from one position to the another, which is equalizing to the changes in the kinetic energy of the body between these systems. This system is basically known as the work kinetic energy theorem. Now let us solve one more question. This question is depicting as a particle is moved along a path ABC. ABC. You will be getting such questions in thermodynamics and chemistry also. Yes. A particle is moved along a path ABC and AOB. AOB. These are the two paths. Now, as you can see, there can be no relation between O and B. They are not direct. Okay. In the presence of this force, the force has been given. X and Y are in meters. Okay. Must be the positions. Find the work done on the particle. Work done on the particle by this force when the particle moves along both the paths. Yeah. Let's frame the equations. We need to calculate work done by the path ABC. We don't know. And then work done by the path AOC. We don't know. Okay. So what will be the work done by the path ABC? It has to be ABC. The body is starting to travel from here, traversing this AB, and then from B to C, it's traversing. So it will be work done in traversing AB plus work done in traversing BC. And then this quantity is standing out to be 0. Why? Because it's along the axis. And when we are calling things along the axis, we have no measurements of work. The body was not moving. You can consider that phase to be the one which is carried on by a coolie who's carrying a load. And because of that theta is equals to 90 degree, the work done is 0 by a coolie. And still he is charging us. Yes. So the force is equals to 3 x square. And now we need to calculate the work done by the BC. It will be 2 by I cap plus 3x z square j cap. Work done by AOB will be the path AO, the same thing which we were writing for ABC. Now we are writing for AOC. And now for AOC, again, we can see that AO is along the axis, so the resultant will be 0 again. Substituting the values, we will be getting 4 because x will turn out to be 4. That means 2 into 2 will be giving you 4. Y is equals to 1. And dy is coming out to be 0. Like this, we will be practicing many of such relevant numericals in my upcoming sessions. And yes, I hope you all understood today's session. Keep practicing, students, and I'll be seeing you in the next time. If you have any doubts, please contact my Urban Pro profile. Thank you so much.